Hello, good evening from Berkeley, California. My name is Scott Stanfield, and I am on the autonomous systems team. I'm the engineering evangelism manager. And we have a lot to talk about, not a lot of time. So we're going to first hear from my general manager, Mark Hammond, one of the co-founders of Bonsai, about some of the announcements that we made today. So we're going to roll a short video, like 4 minutes. I promise when we come back, it's all demo and all hands-on. So with that, let's roll the video.
Hi, I'm Mark Hammond, General Manager for Autonomous Systems at Microsoft. Last year, we unveiled our Autonomous Systems platform, empowering engineers to apply state-of-the-art technology to their physical systems and processes, and showcasing some of the amazing things they'd already created. Today, I'm excited to announce opening these capabilities to anyone to try with the preview launch of Microsoft Project Bonsai. What exactly do we mean by autonomous systems? And how does Project Bonsai help you realize them? Let's consider the evolution of automation, where we can see a steady progression from mechanized systems powered first by steam, then by electricity, which were controlled by manual operation, leading to increasingly capable systems leveraging software to provide automated control for fixed operations, to today's systems, which are increasingly leveraging AI to provide intelligent operation in highly dynamic environments. These systems include a wealth of scenarios across industrial robotics, motion control, machine tuning and calibration, smart buildings and homes, process control and automation, and more. As we look across all of these, a few key common elements stand out. For existing control systems, which are suboptimal, data-centric approaches are proving to not be enough to optimize them, rendering the majority of machine learning techniques insufficient. Rather, deep subject matter expertise and experience are the powerful ingredients that can be leveraged to create successful solutions. And all of these systems must be able to deploy and scale in the real physical world, bridging from the world of bits to the world of atoms. For example, chemicals business SCG has been able to optimize their chemical production process, minimizing loss and reducing calibration and tuning time from months to days to better serve customers' demands. And at Microsoft, we're using our autonomous systems technology ourselves to enhance the HVAC controllers for our campus. To realize these state-of-the-art autonomous systems, we are providing capabilities across 4 essential dimensions. First, we need to harness that deep subject matter expertise and experience. This is realized through a powerful technique called machine teaching. This is a fundamental and powerful shift in perspective. Instead of focusing on how something like the brain or a neural network works, we enable you to instead focus on what you are trying to teach and how best to teach it. This allows you to leverage your deep domain expertise to efficiently and effectively guide the acquisition of intelligence, just as you would for a new employee, in terms that are understandable to you and your colleagues instead of only data scientists or machine learning practitioners. You don't have to know how your team members' brains work to train them, but you do have to use your organization's hard-won knowledge and experience to teach them effectively. Machine teaching gives you the ability to do the same for machine learning. For your system to safely and rapidly gain experience following your machine teaching programs, we bring together powerful professional simulation capabilities from the likes of MathWorks and AnyLogic with the massive scalability of Microsoft Azure, allowing your system to learn across hundreds or thousands of concurrent simulation instances running in the cloud. And we keep you focused on teaching these systems by abstracting away and automating the low-level mechanics associated with the underlying AI. When your machine teaching program compiles and runs, things like neural networks and reward functions are generated automatically on your behalf. And once you've built your controller, we provide the runtime capabilities needed to deploy and integrate it with the rest of your software stack. To help you get started on this journey, we have, in conjunction with our growing ecosystem of partners, created Project Moab, an open source machine teaching robotics hardware kit which allows you to quickly learn via a fun desktop balancing platform. It can quickly go from the seemingly straightforward, but in actuality decidedly non-trivial, to the exceedingly complex, all while enabling you to learn how to harness sophisticated simulation and machine teaching capabilities for your own use cases. The Microsoft Autonomous Systems platform allows you to drive real-world innovation, build trustworthy autonomy, and scale human expertise. Now that we have a sense for what capabilities this technology unlocks, let's dive deeper into exactly how it works. To do that, I'm going to hand things over to Scott Stanfield, Autonomous Systems Community Principal Program Manager. He's going to give us a tour bringing all of these pieces together to create sophisticated control for Project Moab. Scott?
Okay, so you got a little sneak peek of Moab. Let me kind of set up this example. You're at a kid's party and you've got a table of 6-year-olds and they've got paper plates and you've got ping pong balls for some reason. It's your job to entertain them. So you say, just flip them over, throw the food away, hold the plate up to your head, and okay, kids, let's see who can balance the ball the longest. Okay, this is a relatively simple skill. Maybe you have to teach the kids and go over the rules again, like see who can balance the ball in the center the longest without it falling off the plate. And, I, being a human, had gotten pretty good at this. I'm using my binocular vision to look at the distance between the ball and the center and then moving my hands up and down. You get the idea. This is easy. It's actually quite challenging to do this on a machine. And I think that's what makes this very interesting. I'm going to show you this new machine here. This is Project Moab. So what we see is the same plate, and I'm going to put the ball in the middle here and try to balance it with this joystick. So we're in this manual mode. So something that seems, well, we have an engineer, Mike, who knows how to do this really well. But I'm having a hard time doing this because simply translating what I see now into from the joystick to these 3 servo motors it's a complex inverse kinematic problem that I haven't quite learned myself. But for a classic mechanical engineer, actually back up, a classic engineer period, we use the word software engineering, but when I refer to engineers, I'm meaning now mechanical, electrical, chemical engineers. They have a technique called a PID controller. It's a proportional integral derivative controller with 3 magic numbers that are used to determine what gain is needed to reduce that distance over time in order to get this really amazing balancing experience. It's fascinating. It works with nearly any object that's similar in the color, and it can pick up this obloid egg shape. PID controllers are really robust. And it's a good thing they're robust. They're used in about 97% of mechanical systems today. But they're not approachable for someone like me. And frankly, for a lot of the people with simulators trying to solve industrial control problems, you can only go so far with a PID. And I want to show you maybe how we might be able to go farther. And just like we taught those kids how to balance a ball, we're going to teach this Moab unit to do it as well. Now, I have here the one and only clear Moab version. To show you what's inside before we go any farther, there is a single camera, a little Raspberry Pi 4 right here, connected to a custom servo, custom power distribution with 3 servo arms and a fan and a whole bunch of magnets and twisted wires to pass FCC certification. This was designed and built by our fine friends at Fresh Consulting up in Bellevue. And let's take it through its paces. So I'm going to switch over to this demo machine here and show you Project Bonsai. And this is what we announced today. And we have the ability to start with 2 simulations. We have a classic cart pole, and for those of you that may have seen me before holding a broom up in the past, cart pole is essentially an extension. It's an inverted pendulum on the end of a box with wheels, and you have to teach the pole how to stand up. The problem with cart pole is that you need about 6 linear feet and pretty dangerous fast-moving motors. So we wanted to build a similar academic sample, but could sit on your desktop. And so it could sit there so you could train it and learn a lot more about what it takes to build a brain to control system. So I'm going to create a new brain, a control brain today, and I always use the date and a letter. I think we're on G as in golf. So we just have this workspace here. On the left-hand side, we have a list of the brains or controls that I've built earlier today. The default starting point for this teaching parameters here, the language called Inkling, which I'll go over. And finally, the system on the right. Let me start the training right now. This takes a few minutes. So I've just kicked off the training. Well, train it to do what? Let's go back and look at the teaching protocol here. Give myself a little bit more space. And as I'm scrolling through here, there's a few constants that we have in this language. We have the radius of the plate, which is 22 centimeters. We have kind of the first thing that indicates that this is something a little bit different. We have this state. Now, remember earlier I said I could look at the plate and the ball and see where it is relative to the center of the X and Y position. I also can infer the velocity from the simulator. Now, the simulator also exposes two actions. I can change the pitch and the roll, and this corresponds to me moving the stick forward and backwards or left and right. And we've normalized these numbers. So the servo motors would normally be between, like, I think it's 0 and 22 degrees. In this case, we made it easy by going between -1 and 1. So far, we just set up the stage. We have a simulation called MOAB, and it's kind of tucked behind this page right here. And if I go down to the simulation, you're going to see this in a few minutes, but this is the total state that it's exposing. Now, this is a simulator that we built in TypeScript on the front end, and the back end is Python. Now, this is one of our two main simulators that we use for teaching humans about teaching machines. And in this case, it's already deployed, and I have a few instances, it looks like 20, that are going to be running in the background to teach the system. So let me go back to my code. And now we're nearing the core. We've glued our MOAB simulator to our actions and our configuration. But these few lines right here, the goal is the goal here. The goal is taking language and terms that are familiar to a subject matter expert, ranging from, like, say you're a chemical engineer and you're depositing zinc and between a 1 and 2 micron layer on galvanized steel, or you're trying to optimize the supply chain distribution to improve your delivery of quality products in a crunch time like we are now. In this case, I have a pretty simple problem. I just want to avoid falling off the plate and drive the ball to the center. So take a look at these two lines. I can express this as some simple math around the hypotenuse, and the goal is to keep the ball within a range of 80%. But if I go beyond that, the 20%, the ball's probably going to fall off. So anything above that, we'll call that failure, and we'll start over with the training. And likewise with the center, we want to get the ball to the center close enough within about 250 iterations. Now, our cycle time is about 30 hertz, so we get about 250 times before we move on to something new. And then the last bit of Inkling code here is setting up our random starting conditions. Now, I kept these kind of narrow for this build session. We don't have a lot of time, and so we're keeping it to where we're pretending to drop the ball within a pretty narrow range of the center, and we're giving it a pretty small initial velocity. So it's not super challenging. But if you think about the way you might teach another human, the curriculum that you might come up with, let's say it's to hit a baseball. It's a pretty challenging skill. But you would start first by putting a ball in a tee and then picking it up and maybe soft tossing it underhand before you really rear up and throw it fast pitch overhand. And so I'm building up from small steps. So I've started small, and after this, we would improve it to add more features. More steps. So we are training right now. We just got fired up. We have 20 sims connected in the background, running about 180 iterations per second. Now we're trying to satisfy our overall goal, which is a combination of the two sub goals. And if I scroll down, we have this lovely 3D view of the MOAB simulator, the nice shiny. This is the special metal edition, I believe. We can see this one instance of the 20 humming along at different iterations per second, feeding the brain on the back end. And that brain is learning what is the best action to take given a particular pair of ball X and Y positions. Should I roll left or roll right? And so I'm going to leave the velocity out, but you can see this sim is humming along. We would know this is really successful and had settled in once these two lines converge to 0. But you can see all these minute corrections. That's because this is an under-actuated control problem. In fact, it's part of an undergraduate mechanical engineering class. And to solve this with a PID, it's a bit of work. Now, let's see if we can solve it a little bit differently. So I'm going to go back. I have a brain I created literally, let's see, did this one just finish? I did this 33 minutes ago. So part of wow, we hit 100%. So let me stop training this one. And then we're going to move on to the next phase. So we've gone over our Inkling code. We've gone over the training. Now I want to export this brain into a Docker container I can pull down onto MOAB. So now let's go to the bottom left corner of this page. So down in the lower left, you see my list of exported brains. I have, let's see, one I did a little bit earlier today. If I click on while F is exporting, I'm going to grab this Docker pull command. and grab that. This represents a Docker container sitting in my secure Azure Container Registry. And I've previously given the credentials to my Moab unit, which is sitting behind this terminal. And you can see the control loop is performing over here. I'm going to go into my Docker Compose file. And by the way, this is amazing. Like a lot of the code here you see, first of all, we plan on making this, well, it will be open source. We're just waiting for the rest of the bots to show up. And there's some really great practices here, including some code here that Ani wrote around the Docker Compose. And I have to admit, I did not think that I would be doing Docker ever. I kind of like it, and I really like it now because of this feature you're about to see. I'm going to override the brain called custom one. So let me paste this in and delete this one. Okay, so this is the one that we just grabbed, and I'm going to save it. Now, I need to, be gentle with Docker Compose and take it down, but I don't really have the patience. So I just hit Control C, the arms just flatten down. Now I can do Docker Compose pull to go grab my new brain from Azure, and I called it custom one. And boy, that was quick. You guys, everyone must be watching my demo. They're not actually online trying. So let me bring this back up. Docker Compose up. Okay, and we have liftoff. Let's come back around to this camera. And let's see how our brain is performing. So if we can go back to the camera here, and is it running? So let me go into, I called it, grab my mic, I called it custom one, I believe. And there's the brain. Ooh, okay, this is good, because if you recall, I had pretty small initial starting conditions where the ball was closer to the plate in the middle, and the initial velocity was pretty slight. I'm going to show you a brain that was trained that's kind of baked in. This was trained about, I think, a week ago, and I really like it. And this one is incredibly robust. It's very eager. It's like a German Shepherd ready to play fetch. And not only can it balance it pretty aggressively, if I'm good, I can get it to play catch. Watch this. Oh, it stuck the landing. Oh man, I should have been on this camera. Look at that. Let me try it again. That's so awesome. In fact, I have a bunch of ping pong balls here. I thought I would see just what would happen if I threw them all on here. I think it just picks the best looking one. So let's let me show you one more thing. I got a couple more minutes before we have some questions. My friend Paul Stubbs is up in Redmond fielding the questions. Let's see though if I can do one more thing, Paul, before we go to break. So I have a special brain here. Try to show you something that would be very difficult to do with classic engineer controls. I have a special plate that one of our engineers, Journey, drilled a hole into. Thank you. And if I put this on the plate, he gave me a brain. I didn't even look at the source code for it. The brain for this he gave me in the ACR, and I've installed it. And I'm running it now. And this has a really interesting behavior. In fact, wait, let me go back to the classic mode. So this is the classic mode response when there's an obstacle on the plate. It doesn't, clearly the classic mode doesn't know that there's anything here. So if all of a sudden you have this system in the real world and something unusual has happened, you would have to go back and redesign the system. However, we can just add that to the scenario. The Inkling is 5 lines longer. We've included a bit of code to tell it where this obstacle is in space. And now when I put a ball in here, if I roll it just right, it's going to do everything it can to avoid this. And it's a little bit tough to see if I have a top-down camera. I can go around the loop here and try to get it to touch that peg. And I can't quite get it. And it's just this amazing experience. And frankly, I've designed the system so it can be really quiet. So we can just leave it here all day. Occasionally, I will forget it's running. And all of a sudden, I hear the fan kick in, which is a good thing. But understand that this is more than simulations and the application of controls to a mechanical robot-style device. In fact, we really believe the application for the system really far exceeds just the simple control systems. We have 2 very important partners, and we can go back to my demo here. 2 important partners, MathWorks and AnyLogic, that are part of our launch here today. They have built-in support right out of the box for Simulink models and AnyLogic models to do training in the cloud. This is amazing. You could take essentially a zip file of your Simulink world, drop it in here, and instead of being constrained by the resources on your engineering workstation, you could upload the models and do the same training. In fact, there's a whole set of videos that are available on our page, which I'll show after we answer some questions. But you can go and watch the videos of the same Inkling code, but training and running against a MathWorks model. So I think this is a really good opportunity for people like me in the world of development and software and AI to find a way to kind of connect back with the physical world. And it's really the reason I took this job. I've been really excited about taking concepts around AI and how do we reach out into the real world and make things better and improve existing physical systems, find a way to move from atoms and into bits. And I think, well, I know this is going to be a great way to do it. So thank you for watching this. I will be back on again tomorrow at 6 a.m. California time, and then again at 3 a.m. Pacific if you want to see it 3 times. But now Paul's been waiting patiently, and I'm sure there's at least one question.
Hey, Scott. Yeah, this is super exciting. One of the questions I think we have here is, it's interesting that I can do Simulink or AnyLogic, but what if I have my own simulator?
So we have an API. You would expose a couple different things. You need to expose your state through a REST interface. So what kind of, in fact, in this model, I have the wrong screen, but you would hit, I could upload any existing sim that you might have. So you can bring your own for sure. You name it, tell it how many instances you want, as long as you're adhering to our SDK, which is state what actions can you perform and what some other configuration information. And it's really surprising. The MathWorks folks were able to build a simulator of Moab using the CAD diagrams from Scotty at Fresh and got it working in 5 days because
Cool.
they know engineering tools. So they were able to move very quickly. Now, the training and the teaching, it's going to take some time. We're putting this really, really amazing wrapper around some lower level reinforcement learning technology. And we're making it so you don't have to mess around with the hyperparameters and is Apex, PPO. I mean, you can get down to that level if you need to, but really we're trying to bring that technology up a level and allow non-AI experts, but really, the people running the plants. My cousin runs a bread plant. He makes bread and it's an assembly line. And I ask him, what does he try to do with it every day? What's the goal? It's a balance between throughput and efficiency every day. You have raw product coming in, you got bread coming out. And it's a similar problem in other industrial control scenarios. And so they have a simulation, and it's, believe it or not, it's with AnyLogic. And so they can take it and fine tune it to do something, I guess, more bread.
So talking about industrial control systems, how should I think about the diagram or the graph you have on the right as it relates to an industrial control system?
So back on the screen, we've got your face in the lower right-hand corner, but this is well, engineers will be familiar with the concept of a plant diagram. So in control theory, you have your black box, your model of your system, of your factory or your plant, and you have observable state coming out. You have to decide what to do, and you effector action coming in. The difference here is that earlier in the teaching, when we're training it, you saw the loop. But now that loop is cut because I've saved it and I've exported this brain. That means it's baked in. So when it's deployed to Moab, it's not learning as it goes. It's already static. In fact, we have some great technology behind the scenes for us, how we handle stochasticity and taking probability distributions, but that's for another time.
And probably finally, the last question really is, how should I think about Project Moab and then real engineering problems that I may face at my factory?
Yeah. Well, Project Moab is a sample. It's a sample app. It's a tutorial. It's an academic learning exercise. But it's more than that. It's first of all, it was a labor of love for a lot of people and a proof point that we can use RL to train real systems, physical systems in the real world. But it's the on-ramp for our customers and partners. So our earlier customers, SCG, great announcements today that you may have seen in the video. For the partners and customers coming on now, our SIM vendors, our SI partners, and our customers, they will use this Moab tool to learn more about how the product works and to use it as a benchmark for their own skills and improving it and really get into this new, not a DevOps scenario, but an AIOps machine teaching scenario to improve their throughput and how they take these generic skills and apply it to their simulation and teaching.
Cool. And then probably with the last few minutes we have left, can you tell me some more information, some links I should go to learn more?
Why, yes, I have a few links, and I'm glad you asked. There's three. So we'll come back to the demo. And the first is, if you want to learn more about this page, it's aka.ms/Moab. By the way, Moab is a great national park there. There's some rock formation. I'll just leave it at that. So we'll scroll down. You can learn more about here, learn more about what's coming, a little bit behind the scenes. We have this beautiful Sketchfab model. You can zoom in and have an exploding diagram and see all the pieces. It is real, and this is how we built it, but you can learn a lot more about the components. We have some tutorials that would allow you to get started without actually having a Moab unit. So you can balance a ball on a virtual Moab. You can learn how to make your brain more robust, like the default brain through domain randomization. And finally, how to go a little bit farther by avoiding obstacles. Now, this, obviously, we need, the main link. There's really two key things, and I want to make sure this is really important. If you want to learn more, if you want to spend an hour with me or Denise or John Alexander, you can go to aka.ms/as/preview. Don't try to spell the word autonomous. I always blow it. So we have these short links, as/preview. You sign up here, and this looks like one of those kind of generic forms. There's 3 people. We're reading it, not tonight, but we are reading it. You will be hooked in to learn more about if you want to be a customer, if you just want a hands-on tour of the system, if you're a partner and you think you have an opportunity for one of your customers, let us know through this page and we will get back to you. But finally, the main page is aka.ms/bonsai. This was the big launch today. This was the startup in Berkeley that Microsoft acquired over 2 years ago. This is a very important, proud day, and I am super thrilled to be the one to tell all of you about these announcements today, but know that there is a really hardworking group of engineers in Bellevue and in Berkeley and around the world. So we're really, really happy to bring the systems to you. You can go through here and learn more about our customers, some other stories about our kind of where to go next. We really want to give people an idea that they can take their existing skills and their very specific world and their scenario and unpack it in a way that they can bring their simulation, or if they don't have one, we can help hook them up with a partner that can, but bring it into our platform and teach it to do more. And we believe that starting today, we have a way to make this exposed to a very broad group of people, and we'd love to have you along for the ride. So again, quick links are aka.ms/bonsai, which you saw here, aka.ms/Moab, which is our teaching tool here, and finally, the link to go sign up, aka.ms/as/preview.